we're going to talk about three-phase Y motors seen as an RL circuit. This is AC theory, but we're going to talk about a motor anyway. Here's my slide. Okay, we're going to look at just a Y dual voltage, 9-lead motor, which should be becoming familiar now. And we're going to look at it hooked up as a high voltage circuit. Okay, so we know that we've got 480 across this thing. And since it's a Y, that you know that each phase is getting 277 volts. And let's look at that. So here's the black phase, phase A, is going across winding 1,4,7,8. That's not 7, 8. That's 7 central point, 9, 6, and 3. You see it forms a series circuit across 2 sets of windings. Now the red phase does the same thing across 1, 4, 7, 8, 5, 2. And then the blue phase will go across 2, 5, 8, 9, 6, 3. So you can see there are 3 separate phases happening at slightly different times. Now, we don't want to look at it as just a winding, because we know that a winding looks like as a resistance, a pure DC resistance, and an inductor, right? So we're going to look at this motor, and we're going to look at this thing as an RL circuit, okay? So let's go down to that. And we're just going to look at one phase, because we want to stay in phase, right? Every time you do something with transformers or motors, either one, when you're playing around with three-phase, you want to look at a single phase and find out what's happening. So let's just look at the black phase. And we're going to say that we have a few pieces of information. Okay, so we're going to plug in a few things that we know about this motor, but we're looking at the moment, we're looking at line totals. So we're looking at the fact that it's a 460-volt motor. It's operated at 34 amps, and that means that the total impedance is 13.529 ohms, and its total incoming power is 15,640 VAs. Now that gives us a triangle, doesn't it? All right, so now let's look at these things in a triangle. And let's look at what we have. We have, as a phase total, we have 27,089 VAs, 460 volts, 34 amps, and 13 something ohms is our impedance, right? Those are line totals. Let's look at our phase total. Let's go back to our triangle here. I should say our Okay, so let's look at this. Our line total, now remember our Y rules. What's our Y rules? Our current is constant. So if we want to look at just one phase, we can do that. Okay, but we've got to look at what are our line totals. So when we look at this one phase, we know that it's still got 34 amps of current, right? Because it's a series circuit, right? But what is our voltage? Our voltage across this is 277 volts, right? 277 times square root of 3 is 480 or something like that. So it's not exactly 277. It's 277 divided by 1.7321. No. Do it again. It's 460 divided by square root of 3.
I'm sorry, I thought you said 460. I mean 270.
No, sorry, I said the wrong thing then. Which isn't that unusual.
265, 65.
There we go, 265 volts. So we've got 265 volts here. We still got 34 amps. But now we have phase totals. Much handier. Okay, so let's go over here. Okay. So we have 265 volts on one phase. We know that it's 34 amps is still our current flow. So from that, we can find that our phase resistance, our total impedance, our XL and our resistance together are 7.79 ohms, right? Everybody agrees with that? Okay. And our total apparent power is 9,010 VAs. Now, the reason our resistance, our impedance, is different from half of the total resistance of the line is because they're different by square root of 3, not by 2. Okay, so it's odd to think about resistance not being this one plus this one is the two of them, but again, AC is a little different, especially when we're talking about three-phase power. Now we want to talk about our phase angle. Where could you think we could get our phase angle from? When we did it before, we found that our total apparent power was 27,000. $0.89, is that right?
Yes.
Okay, that was a total apparent power, right? And we also found our total true power, which I think now when we look at the power triangle, we know that the cosine of the power triangle is the true power over the apparent power, right? So that would give us the cosine of our angle, would it not? Okay, so let's pull out our handy dandy TI-30X2S and let's put that in. Second function cosine 18,650 divided by 27,089 and find out what is our phase angle. What is it?
46.49.
Ooh, that doesn't show up very well. That doesn't show up very well either. Oh well, 46 point what? 49, 46 and a half degrees about, right? Okay, now is that the same angle as the phase? That's the line phase angle, right? But the phase angle is the phase angle is the phase angle, right? Okay, so we can say that we know the impedance of this thing right here. That's our impedance. Goes right here. If that's true, we can find our resistance, can't we? Okay. So what is my resistance of this motor? Okay. We're back in the cosine. We've got the cosine. The cosine of this thing is 18,650 divided by 27,089, right? Okay. And that times, the cosine times the hypotenuse will give us the adjacent, right? So let's multiply 7.79 times 18,650 and divide by 27,089. What would we get? 556. Okay, that's a good thing to know. That's handy. But what we really want to know is what XFLs do we have? And to find that, we need to take the cosine of 46.49, right? No, the sine. We need to take the sine because the sine is O hell. And we multiply OH by times H, we'll have O left over, right? Okay, so let's take the sine of 46.49 degrees and multiply that times 7.79. And what do we get?
5.165.
That's our x of L. Now, why do we want to find that? Oh, because we'd like to power factor correct this thing, wouldn't we? Ah, so what we know now is if we use this motor as it is, we'll be paying 30,000 VAs for about 19,000 VAs. In other words, it's going to be about what? 67% efficient? I don't think anybody would agree that 67% efficiency is a good thing. Right? So what would we want to do to this thing? We want to get rid of 5.65 ohms of X of L, right? How do we do that? We add a capacitor that's somewhere near that in parallel to this circuit, this motor, and it will power factor correct it. Right? Okay, now we need to talk about one more thing before we go on. How do you add up three-phase power for three different motors? Can you add up just the apparent powers? No, because they're inefficient motors, right? Okay, so let's do that next. Let's look at, because we can see what we're going to do here, right? We're going to change this power factor. Everybody see that? Okay, so what we want to do is figure out how we can add up the power for three different motors.